So let's look a little more at this new way of talking about the wedge product, the epsilon. The claim is that we've got this really cool identity. It turns out to be really useful in sort of more advanced presentations and when you get into differential geometry. That if you anti-commute these guys, if you look at this and you look at the sum in the two orders as an operator, it's just multiplying alpha by the scalar, which is the dot product of u and v. This is really just a restatement of the derivation identity for the interior product. Because if we just expand this out, remember the epsilon was just an interesting notation for wedging in a, it's wedging in v tilde, because we've got to make it a form. That's a tilde. Okay. So it's just, oh, look, we're interior product of a vector with the wedge of something. Oh, okay, we know how to do that. That's interior product it with the first one and leave alpha alone, and then minus just take v tilde, wedge this guy. Oh, and then add it back in. Okay, and they cancel. Okay, now what is this? This is a one form or a vector interior product into the tilde of a vector, and that's exactly the dot product coming up. Okay, so this is another way to state basically that derivation identity, or at least where this guy happens to be a one form and expressed as a tilde of a vector. But that's probably the most important case. Okay, let me just give you a couple consequences of that. It's just really just a tease for a lot of stuff you could do with it. First of all, if you apply it, let's apply it at the bottom and the top. Always, it's good to look at the bottom and the top. If you apply it to the bottom, that is just to the one, just to the number 1, the 0 form 1, well, this guy just dies because that becomes a minus 1 form. It just goes to 0. Epsilon u on 1 is just u, ooh, that's a v. Yeah, that's a v, sorry. Epsilon v on 1 just means wedge in v tilde to 1, so you just get v tilde. And then it's the interior product of that. Okay, yeah, certainly. That's just going to be u dot v times the scalar 1, which is just u dot v. Okay, so it says that it's just giving this guy on u dot v. Okay, and on the top, it's let's look at this acting on the volume form. Okay, so let's see what's going to die here. If you got the volume form, that's already the highest degree form we can get, so we're not going to get that guy. Okay, and so that's going to be v tilde wedge iu dv. But I mentioned earlier that if you interior product a vector into the volume form, that's the way to take u, turn it into one form, and then star it. Okay, and then that's going to be v tilde wedge that guy. So one of the properties of the wedge that I've talked about in other videos, in the intro to differential form videos, is that one nice characterization about the star is that if you take two forms of the same degree, namely these two one forms, take one and don't star it, but wedge it with the star of the other, then that's exactly the inner product of these guys as forms times the volume form. Okay. Oh yeah, that's exactly what we were supposed to get. That's again the identity. This is supposed to collapse into the inner product. So it's a double check that not only does this come from the derivation identity, it makes a lot of sense with stuff we already know, at least at the top and bottom of the ladder. Okay. Now here's a very cool thing that's a tease for some more sophisticated stuff, which I might allude to briefly later, but I thought about doing more on this, but it would just be another whole sequence of videos. Okay, so I'm going to define one more operation, the C operation, and it's just the sum. Ooh, actually, now let's take the difference. Some people like the sum, some people like the difference. I'm going to use the difference. Is the difference of the epsilon and the I. And what's weird about this, what's kind of new and novel about this, is that this purposely will give you an inhomogeneous form. if alpha is a p form, this will be something that's a p plus 1 form and then subtracted a p minus 1 form. You can totally do that. It's totally legal, but it's a little bit more complicated to deal with these guys. Okay. Notice, though, if this has even degree, these will both have odd degree, and if this has odd degree, these will both have even degree. So the parity of the degrees is the same, but the degrees will not be the same on these guys. Okay. So here's what I want you to think about. Another good place to pause the video. What you want to show is that let's do the same thing. We keep doing this thing of let's look at what happens when we anti-commute these guys, okay? This would be 0 if they anti-commute. And it's like, well, gosh, everything so far has anti-commuted. If you do this with D, if you do it with IU, if you do it with epsilon U, the whole point of all this algebra, right, is all this anti-commutative stuff. Isn't this just going to be 0 again? Well, no, it's not. It's going to be minus 2 U dot V. Or in other words, if I take this, and to make it a little more explicit, if I act with both of those on alpha, it's again a scalar times alpha, and now it's just minus 2 times that. Okay? So, you might want to pause the video before I show that. Okay? It's really easy, though. It's just expanding this out. Epsilon V minus IV, epsilon U minus IU. Okay, now what's going to happen? Epsilon U epsilon V plus epsilon V epsilon U, those do anti-commute, so that's going to die. And then this is going to be a plus IU IV plus another IV IU. Those also anti-commute, and those die. Okay, so the only things that don't die are minus IU epsilon V minus epsilon U IV, and then another minus IV epsilon U, and minus epsilon V IU. Now I recollect them. Ooh, look at that. Let's see, which ones are recollecting here? It's these guys. Okay. This is exactly the combination we were talking about before. I'm just anti-commuting. They both have a minus sign. I'm just adding together epsilon U and IV, okay? And here, I've just got an overall minus sign times epsilon V switched around with the IU. That's an I. It doesn't show up very well, okay? And so I just get 2 of what I got from the product identity, okay? So why is that so cool? Well, I can give you a tiny taste of it, okay? This is the first time we've done this cool combination, which seemed to be so important, and gotten something other than 0. And in particular, if I look at CU squared, we noticed that D squared and IU squared and epsilon U squared, those all square to 0, which is very cool. That's a very useful thing to have. But this guy, this is just going to be 1/2 of this expression with the V set equal to U, and so that's going to be minus U dot U. Or in other words, minus the norm of U squared. Okay. Turns out that there's a beautiful calculus analog of this that I am going to make another video about at some point, fairly soon, hopefully. It turns out that this is, the calculus analog of this is the Laplacian operator. And in fact, even the minus sign being there is a good thing. It turns out there's some funky minus signs when you think about derivatives in a certain way. And this is actually analogous to the Laplacian. You can kind of see that. This is, u1 squared plus u2 squared plus up through un squared in n dimensions. The Laplacian is d squared by dx1 squared plus d squared by dx2 squared, etc. There's a formal analogy that you can make much more than formal. And so turns out that this, the analog of this in terms of derivatives, would be the square root of the Laplacian operator in a certain sense. Something that if you do it twice, you get the Laplacian, but is in itself a very interesting operator. It turns out to be what's called a Dirac operator. Intimate connections to quantum mechanics, quantum field theory, this theory of spin in quantum mechanics, and some beautiful, beautiful mathematics. Maybe some of the best mathematics. Well, definitely some of the best mathematics of the 20th century. So that's a good place to stop this video. And I think I'll make maybe one more on this line before I switch to the third view. But that's a good place for now.